So for problem number 4, we are from a 12 by 12 inch piece of metal, squares are cut out of the four corners. And so we've done these a few times, these kinds of problems. And we know that X then would represent the height of the box. So fold up to make a box. So the sides, yeah, so it's an open top box with a height of X. And then remember, if we start with 12, and we subtract an x from each end, one side of the box would be 12 minus 2x. In fact, both sides of the base of this box would be 12 minus 12x. X represents the length of the sides of the square in inches that are cut out. Okay. Express the volume of the box as a function of x. So volume in terms of x is length times width times height. Length times width times height. We're going to put the height first, and then we're going to be kind of tricky here, and instead of writing 12 minus 2x twice, we're just going to write 12 minus 2x quantity squared. Express the volume, we've done that. Check. What x value maximizes the volume? And we're just going to use Desmos or our graphing calculator. So if we type in x times the quantity, 12 minus 2x quantity squared, and let's adjust our viewing window. So our window, the lowest value x could be would be 0. The highest value, think about this, if you only have 12 inches to work with, and then if you took 6 inches from one end, then you'd only have 6 inches from the other end. 6 and 6 make 12, so we can't go more than 6. We can't take more than 6 away from one end. So we can even lock in a low x max, so we can really hone in on what our volume is going to be, and not be distracted by a graph that goes outside of these parameters. The lowest the volume could be would be 0, and not really sure how high to make the volume. What 6 times 6 is 36, and then I don't know, let's just put 200. It's probably way too high, but not too bad. So here we have our volume function. In fact, if we trace it, we can see if the length of each of the squares is right around 1, you can see perhaps the coordinates moving around there. If the x is right around 1, is it inch? Yeah. 1 inch, the volume would be about 105. But if we take a little bit more than 1, right around 2 it looks like, right around 2, then we're going to get a maximum volume. So our maximum volume looks like it's hovering right around 128. Okay, approaching 128. And so we would just do this the same way we did the other one. So second, calculate maximum. And we mark the left side of that high point. Mark the right side by hitting enter. And then we just back it up a little. You don't have to even get close, just be in between. Oh, so it looks like this could have been one that we may have been able to solve by hand, because the x is 2 and the y is 128. So let's see, what x maximizes the volume? And the way you would show your work on this one would be kind of like that. You would put the ordered pair 2, 128, and that 2 represents the x. The x that maximizes the volume would be 2 inches. And the maximum volume, be careful here with the units, the maximum volume would be 128 cubic inches. Okay, and that's how you do that one. So the hardest part about solving these kinds of problems is actually, as you may have already noticed, creating the function. But once you get the function, just type the function into either Desmos or your graphing calculator, and then find either the maximum or the minimum, whichever the problem calls for.